Okay, I'm going to start off this video on momentum and impulse with a comic strip. One of my favorite comics growing up was Calvin and Hobbes. So here's Calvin, and he sneezes. Achoo! Phew, no brains. Achoo! The force of the nasal explosion sends Calvin reeling through the stratosphere. With less and less air to resist his momentum, he breaks the pull of the Earth's gravity and hurtles past the moon. As he passes out of the galaxy, Calvin reflects on the wisdom of covering one's mouth when sneezing to deflect the propulsion. Alas, it is knowledge gained too late for poor Calvin, the human satellite. But wait, another sneeze is brewing. Calvin turns himself around. The second sneeze rockets him back to Earth. He's saved. It's a miracle. Achoo! God bless you. Oh, he does, Mom. He does. Okay, what's happening in this comic strip? Obviously, it's a little bit far-fetched. A sneeze doesn't exert enough force to launch you into orbit. But the concept is still interesting in looking at. So what's happening here is that the sneeze is exerting a force in one direction, right, in this direction. But according to Newton's laws, there has to be an equal but opposite force. So there is a force on Calvin in this direction, right? Now the sneeze really is a relatively small force, but we're exaggerating things here and pretending that he can exert a really large sneeze and have a very large force pushing him in that direction. So we know that a force will cause an acceleration. And we know that acceleration is equal to change in velocity over change in time. And it's this form of the equation that Newton actually used when he was expressing his second law. He didn't call it acceleration. He talked about change in velocity. If we rearrange this equation slightly, bring the time over to this side, we see that we get force times time equals mass times change in velocity. And this concept right here, mass times velocity, is something called momentum. We give it the symbol P, and it's the mass times the velocity. And momentum is just a property of matter, like any other property, like mass or color or size. The momentum is the product of the mass and the velocity. So again, if we looked at the units, it's the kilograms times meters per second. So momentum is measured in kilogram meters per second. So really it's how much mass and how fast is it moving. So obviously you can have a very small mass, like a housefly, which doesn't have a lot of momentum. If it flies into you, you don't really feel it. But another mass, like say a bullet fired from a gun, has a relatively small mass, but if it hits you, because it has a high velocity, it has a lot of momentum. Okay, so it exerts a bigger force, right? More momentum, more force. And that's what's happening here with Calvin. His sneeze is apparently exerting a large force on him, causing a large change in velocity, right? And he ends up rocketing out into space. Eventually he turns around when he feels another sneeze coming on, and he exerts a force in the opposite direction, so sneezes in the opposite direction, and that causes his velocity to change backwards, and he comes back to Earth. Now, this concept of change in velocity or a change in momentum is also known as impulse, right? Mass times change in velocity will equal a change in the momentum, and this is known as impulse. Not impulse like I'm a very impulsive person, but impulse in terms of change in momentum. And you might have heard the term impulse used in this term before, in this way before, if you've ever watched Star Trek, right? The Starship Enterprise has a warp drive for traveling faster than light, but it has an impulse drive for traveling just at regular speeds. So the engine on the Starship Enterprise is really just a change in momentum drive. They called it an impulse drive because it had a more scientific sounding name, makes it sound fancier. This concept of impulse is also why we have airbags in our car, right? The airbag causes the change in momentum to occur over a longer period of time, right? So if I hit the steering wheel, I would come to a stop quite suddenly. But because I hit something that's softer, like an airbag, the time that the collision takes between me and the airbag, as I cause the airbag to compress, that longer period of time means that the airbag exerts a smaller force compared to hitting the steering wheel. Right? So by increasing the amount of time, I reduce the amount of force. This is also why we bend our knees when we jump. Right? If you jump and keep your knees locked, you experience quite a sudden feeling of force on your body. But if you bend your knees and cause that change in momentum to occur over a longer period of time, you experience less force. Okay, so the other thing to note, force obviously is measured in newtons, time is measured in seconds. So 1 Newton second is the equivalent of 1 kilogram meter per second, right? These two units are the same, so we can have impulse expressed in Newton seconds or kilogram meters per second. The other thing we should note is that momentum, because it's the property of mass and velocity is a vector quantity, the momentum is also a vector quantity. Meaning that the direction of the momentum is important. The direction of the velocity and the direction of the force on our impulse are important. Meaning that impulse and momentum can be either positive or negative, right? In the positive direction or in the negative direction. So when we're adding and subtracting momentum vectors, we're going to have to remember to add them as a vector diagram or to break them down into their components. Okay, there's lots of good examples on impulse in the textbook. Hopefully you have had a chance to try some of them. And in the next video, we're going to talk about the law of conservation of momentum. And that's going to be very similar to the law of conservation of energy that we just talked about, but we have to remember now that we're dealing with vectors. So it's going to be slightly different.